Welcome to my webinar. My name is Professor Alison McConnell. This presentation was made on November 20th, 2013 as part of a series of webinars organised and sponsored by Human Kinetics Publishers and the British Association of Sport and Exercise Sciences. If you'd like to know more about inspiratory muscle training after the webinar, further information is available in my 2 books, each of which is supported by a dedicated website. It's perhaps particularly appropriate that I'm speaking to you today on what is World COPD Day, because inspiratory muscle training is an intervention and management tool that's been perhaps most widely used in this particular group. Now, I'm not going to talk about patients with COPD today, but I just wanted to make you aware that inspiratory muscle training has much wider applications than in healthy young athletes. Now, I'm aware of the diversity of backgrounds and interests of the people who've logged in today, and so I've tried to prepare my presentation in such a way that I hope that I've got a little bit of something for everyone. So for the hardcore physiologists, but also for the practitioners out there. Now, in terms of the structure of my talk, I've broken it down into different sections. The first thing I'm going to do is to describe the muscles of respiration, and also perhaps to enlighten you about some lesser known functions, if you like, of these muscles. And this has a direct impact on how we should train them. I'm going to talk about what these muscles do in the context of particular sporting movements. I'm then going to talk about the nitty-gritty, if you like, which is how we go about training the inspiratory muscles in particular. I'll describe what happens when we undertake that kind of training. I'll talk also about why we get the responses that we do, particularly in the context of performance, so some mention of underlying mechanisms. I'll also explain why I think that inspiratory muscle training is probably the easiest and quickest way that anyone can improve their performance, and I'll provide you with some evidence to support that contention. And then towards the end of the presentation, I'll wind up with perhaps something that's a little bit more practical, and I'll talk about the application of functional training techniques to the inspiratory muscles, having, I hope, laid the groundwork for establishing why I think functional training is the way to go. And then, of course, at the end, there'll be time for your questions. Now, for many, inspiratory muscle training still sounds too good to be true. Now, I'm hoping to suspend your disbelief fairly early on in the presentation by quoting from the foreword of my book on inspiratory muscle training by one of the UK's leading Olympians and world champions, that is Sir Matthew Pinsent. He won 4 gold medals at successive Olympic Games in rowing, and what Matthew has to say about breathing training is illustrated in this slide, so I'll read it for you. Advances in sports science knowledge are few and far between. Amongst these rarities is the discovery that breathing has such a profound influence on performance that it merits specific training. So I hope you'll take the word of an Olympic and world champion, and we'll go along for the journey into inspiratory muscle training with me with an open mind, if you are indeed one of the skeptics. Now, one of the things that people often say to me is that they breathe 24 hours a day, 7 days a week. They've done it since the day they were born, so surely they're an expert on breathing. Well, in much the same way that we can all breathe intuitively, we can all lift weights, we can all cycle, we can all run. But in the same way that we can lift a weight very badly and inefficiently, we can also breathe inefficiently, and we can, to some extent, make our lives more difficult by not training specifically for the act of breathing. There are a number of advantages in doing this, and I'll explain those as we go through the talk today. Now, you may think that lifting a weight is complex, but in fact, breathing itself is a highly complex muscular process, as illustrated by this diagram here. I've color-coded the muscles here just to illustrate the complexity of the muscles that are involved in breathing. Now, one of the striking things about this diagram, I think, is that if you look at these muscles, they pretty much encompass the entire trunk. So muscles that you would think of as being trunk muscles are actually have a primary function in respiration. Now what I've done is I've divided the muscles here. Those on the left are inspiratory muscles and those on the right are expiratory muscles. So the active breathing is a fairly simple bellows process, if you like. In order to inhale, we contract our diaphragm. That flattens the diaphragm, moves it down into the abdominal compartment and expands the chest volume. That causes a pressure differential and air moves into the lungs. We also have accessory muscles of inspiration in the rib cage and in the neck, and those also serve to expand the chest. And they make the diaphragm more efficient by stiffening the chest and making the chest wall more resistant to the collapsing pressure that the diaphragm could exert. Now most of the work of breathing at rest is done by the inspiratory muscles. So you take a deep breath in, all you have to do at rest is to relax those muscles, and the act of expiration occurs via the elastic recoil of the system. And now during exercise, of course, we need to increase ventilatory flow. In order to do this, we not only need to make more forceful contractions of our inspiratory muscles, but we also need to activate our expiratory muscles to increase expiratory airflow. Now the main expiratory muscles are the muscles of the abdominal wall. Now the way that they bring about expiration is twofold. Firstly, some of them are attached to the rib cage. So rectus, for example, is attached to the lower rib margins. If I show you here, is attached to the lower rib margins, and that actually pulls the rib cage downwards, compressing the thorax. We also have the transversus abdominis and the oblique muscles, and those compress the abdominal compartment, and in doing so they push the non-compressible mass of the abdominal organs up against the diaphragm, pushing the diaphragm back into the chest and increasing the pressure inside the chest. So that's how breathing is brought about. Throughout breathing, whether it's at rest or during exercise, there is always some elastic energy that is gifted to exhalation by the action of the inspiratory muscles. So a greater proportion of the work of breathing is undertaken by the inspiratory muscles than by the expiratory muscles. Now those are the respiratory functions of the muscles. What I want to describe for you now is perhaps some lesser known functions of the respiratory muscles. So for example, the diaphragm is a muscle that is involved as a part of the core stabilizing system. Now of course our expiratory muscles are the muscles of the abdominal wall, so they're implicitly core stabilizers. But our diaphragm is perhaps a lesser known participant in core stabilization. Now if our transversus abdominis and obliques contract in order to increase the intra-abdominal pressure and generate pneumatic pressure that stabilizes the spine in particular, were our diaphragm not to oppose that increase in pressure within the abdomen, the pressure would be dissipated and the effectiveness of these muscles in terms of promoting core stability would be diminished. So we can think of the diaphragm as being the lid, if you like, on that core stabilizing box. So it's a very important part of the pneumatic support structure that maintains trunk stiffness and protects the spine from injury. Now part of this process is stiffening the trunk, and it doesn't just involve the diaphragm, it also involves the muscles of the rib cage. Now in a sport such as rowing, most of the muscles that are producing the force are below the waist. However, the force generated by these muscles has to be transferred via the arms and the hands to the blade handle, either on this ergometer or to a blade which is in the water. Now if the trunk is not maintained stiff, then there will be leakage, if you like, of the force that's being generated by these main propulsive muscles before it can reach the blade handle. And that leads to mechanical inefficiency and loss of performance. So the respiratory muscles, the diaphragm and the muscles of the rib cage, are important stiffeners of the trunk which are involved in sports such as rowing, for example, a very obvious example. Now the muscles of the rib cage in particular, and of course the obliques, are rotators and flexors of the trunk. And here we can see a well-known golfer. You can see that although there is rotation at the hips, there is also a lot of rotation occurring within the trunk. And that rotation is brought about by the obliques, which, as I mentioned, are expiratory muscles, and also by the rib cage muscles. So they're involved in rotation and flexion. Now, a function that you might perhaps, again, not necessarily associate with respiratory muscles is their role in postural control, in maintaining balance when we're running over uneven surfaces, for example. And fatigue of those muscles is also associated with lack of postural control and perhaps an increased risk of falling. So these muscles are involved in a wide range of activities that have an influence on sports performance, not necessarily in pure performance, but in terms of other factors that would contribute to performance. Now, this is something that I can identify with personally, and I'm sure that many of you out there also are aware that when you run, you're often more out of breath at an equivalent intensity of exercise than you are when you cycle. And if you don't experience this personally, and I would be surprised if you don't, but if you don't, you may experience this with clients, for example, in a personal training context, where equivalent heart rates correspond to quite different intensities of breathing effort and breathlessness and associated exercise limitation. Now, why is this? Well, it's because when we run, our torso, our trunk, is unsupported, whereas when we're cycling, the trunk is in a supported position, and so the respiratory muscles of the trunk can, if you like, concentrate more on breathing than their non-respiratory function of postural control and stabilization. So this conflict, if you like, is epitomized by running, and the fact that running makes you more out of breath than cycling. Now, given the ubiquitous involvement of the respiratory muscles in so many different activities, from both a respiratory and a non-respiratory perspective, this raises the question about their fatigability. Now, for many years, it was thought that the inspiratory muscles, and in particular the diaphragm, were relatively resistant to the effects of fatigue by virtue of their continuous activity throughout life, the fact that they have a highly aerobic phenotype, they have a good blood supply, and as a consequence of that, there was an assumption that the diaphragm especially was not susceptible to fatigue. However, we now know, there's plenty of evidence, using both voluntary measures of inspiratory muscle function and also robust electrical stimulation techniques involving the diaphragm, that these muscles do fatigue. Now, this is just an example of some of the situations and the magnitude of fatigue which is encountered. These are all published data. This is data from incremental running to the limit of tolerance, a bleep test if you like, so it's an incremental shuttle running test. This particular study was in elite rugby players, professional rugby players, and at the end of the test, their ability to generate inspiratory pressure was diminished by 10%. Following rowing, this is a 6-minute all-out piece on a rowing ergometer, a 12% reduction in inspiratory muscle strength. Following cycling, depending upon the distance covered, 20-kilometre time trial 13%, 40-kilometre time trial 19%. This is where the numbers start to get a little bit concerning. Following swimming, and this was 90 to 95% of race pace, a 200-metre front crawl swim in age group swimmers. So this was a swim that lasted less than 3 minutes, and what we observed was a deficit of almost a third in inspiratory muscle pressure generating capacity. Now, swimming is a fairly unique environment. We have the hydrostatic pressure, which opposes the movement of the abdominal wall and the rib cage, but we also have what I call respiratory gymnastics, particularly in front crawl swimming, where the pattern of breathing is highly unnatural. It's quite disrupted, and as a consequence of that, it's quite fatigue-genic. So we now know that inspiratory muscles are susceptible to fatigue, and in sports related contexts, so following time trials, for example. Now the next question is, does it matter? Does it matter that these muscles fatigue? Well, one way of looking at this is to pre-fatigue the inspiratory muscles and to see what then happens to performance. Now, a study was undertaken in the early 1990s, almost, well, more than 20 years ago now, to examine this specific question. And they undertook 3 exercise tests. It was high intensity exercise to the limit of tolerance. You can see it was high intensity because the limit of tolerance was occurring within 300 seconds. So we had 2 tests where the participants began the cycling test unfatigued, so that's control 1 and control 2. And then we have another test where the inspiratory muscles were pre-fatigued by having the participants breathe against an inspiratory load. And what they observed was a 23% reduction in the ability to sustain exercise, so they could sustain exercise for 23% less time. Now, another feature of the inspiratory muscle fatigue was that it made the exercise feel harder. So this is a visual analog score rating of exertion at the beginning, middle and end of the cycle test, and you can see that under the fatigued condition the rating of perceived effort was greater, significantly greater at the middle and end of the test following the pre-fatigued condition. So fatigue of the inspiratory muscles impairs performance and it increases effort, and of course those 2 things are interrelated. So the question is, how do we overcome these phenomena? How do we overcome inspiratory muscle fatigue? Well, I suppose the clue is in the name of the slide and the presentation, in that this is a presentation about inspiratory muscle training. So let's have a look at inspiratory muscle training in a little more detail, and we'll find out its effect on inspiratory muscle fatigue in a few moments. So a number of years ago I termed the phrase dumbbell for your diaphragm, and this refers to the application of tried and trusted resistance training principles to the inspiratory muscles, and we can do that using a relatively simple piece of equipment. This is an inspiratory muscle trainer. The dumbbell, if you like, is this spring-loaded valve. Now we can change the opening pressure on the valve by compressing or relaxing the spring using this threaded tensioning knob here. So this accommodates for different starting abilities, and of course also enables one to develop progression within the training as the inspiratory muscles become better trained and stronger. Now exhalation is unimpeded and it occurs through this one-way flap valve here. But in order to breathe in, you have to overcome the tension on the spring by generating sufficient negative pressure in here, which is produced by your inspiratory muscles. Now, what kind of training are we talking about? It's relatively simple. It involves a relatively inexpensive device. It's simple, so it must be hard, of course. Well, no, it doesn't have to be hard, and in fact this is one of the easiest forms of training I think anyone can undertake. We now have evidence that effectively we can improve the inspiratory muscle function using moderate intensity loads repeated for 30 breaths twice daily. So moderate intensity corresponds to around about 50% of inspiratory muscle strength, and that actually corresponds to the 30 repetition max of the inspiratory muscles. Typically we would see improvements in strength of between 25 and 45%. Power output improves by around 60%, and endurance improves by a similar amount, although in some studies endurance has been shown to improve by 100 or even 200%, depending upon the particular population being studied. And these changes occur within 4 to 6 weeks. Now, question is, are these genuine physiological changes? Well, here's a study that helps us to understand that. We have a 4-week inspiratory muscle training intervention using the tried and trusted training protocol that I just mentioned, so the 30 repetition maximum twice daily. You can see that there's a rapid improvement in inspiratory muscle strength, which is on this axis here. This is the inspiratory maximal pressure, which becomes significant at week 2. Now in this study they also measured the thickness of the diaphragm. Now this can be done by using ultrasound, and you can image the diaphragm relatively easily through the chest wall at what's known as the zone of apposition. So the diaphragm sits up against the inside of the rib cage in what's known as the zone of apposition, and you can image the diaphragm relatively easily using ultrasound at this location. Now here we can see the results in terms of an ultrasound scan, and even on visual inspection you can see that the thickness of the diaphragm is improved as a result of this 4-week training intervention. So what we have here is hypertrophy. We have structural remodeling of the diaphragm in response to resistance training. And really we shouldn't be surprised. The diaphragm is the same as any other skeletal muscle. If you overload it, it will respond with a training adaptation. And in this case, because the training stimulus was a resistance training stimulus, it has responded with hypertrophy. Well, that's all well and good. We know that we can improve inspiratory muscle function, but what happens to exercise performance? Well, this is a study that we conducted over 10 years ago now. It's published in 2 parts. It was published in 2 parts because it was a very comprehensive study and still remains the most comprehensive study of inspiratory muscle training and its effects on time trial performance. Now we tried to design the study in such a way that it was as rigorous as possible. It was a double-blind, placebo-controlled design, so neither the principal investigator who was making the measurements nor the participants knew whether they were in the real training group or the placebo training group. Now we rigorously monitored all of the training undertaken by the athletes, so not just their inspiratory muscle training but also their whole body training, because we wanted to make sure that any changes that we saw at the end of the intervention were not due to their whole body training and that they could only possibly be due to the inspiratory muscle training. How did we monitor the IMT? We did so by instrumenting the mechanical inspiratory trainers such that we could identify the opening of the valve of the device, so we knew how many breaths effectively, how many repetitions had been undertaken. Our participants were 16 highly trained competitive male cyclists. Unfortunately, Bradley Wiggins wasn't one of them, but it's a nice photo nonetheless. The intervention lasted for 6 weeks. We used our tried and trusted intervention of 30 breaths at 50% of the inspiratory muscle strength. That was our real training group. Our placebo was 60 breaths at 15% of inspiratory muscle strength. Now that's sufficient for you to perceive that you're breathing against a resistance, but we know that it's not sufficient to induce any improvements in inspiratory muscle function. Now the real training group were told that they were a strength training group, and the placebo group were told that they were an endurance training group, and in that way the placebo was maintained. Now obviously we monitored their inspiratory muscle function, not just strength, we also monitored power and endurance. We also assessed the magnitude of exercise-induced inspiratory muscle fatigue to see whether this was attenuated by the training. We undertook a maximal incremental cycle test, so a VO2 max test effectively. And finally, perhaps most importantly from an external validity point of view, we undertook 2 simulated time trials in the laboratory, one of 20 kilometers distance and one of 40 kilometers. And in our participants, they were about half an hour and an hour in duration. Okay, well, what did we find? Well, we found no difference either between the groups or within the groups in their whole body training. So there wasn't any difference between placebo and IMT in terms of the training that they undertook, and there was no difference across the intervention. We had very good compliance to the training and also obviously to the placebo training. Our inspiratory muscle training group, our real training group, improved their inspiratory muscle strength by 28%, and that was statistically significant, and there was no change in our placebo group. There was no change in lung function. Now lung function is a bit like leg length. You can't actually improve your lung function unless, of course, you have diseased lungs or you have profoundly weak inspiratory muscles. So lung function is not improved. Similarly, maximal oxygen uptake is not improved, and I'll elaborate on that in a few moments in terms of why that's the case. We also saw an attenuation of the magnitude of exercise-induced inspiratory muscle fatigue, but only in our inspiratory muscle training group. And in terms of the improvements in performance, they're summarized in this bar chart here. Here's our placebo group, and this is for the 40-kilometer time trial, before and after the inspiratory muscle training, and you can see that there is no change. In contrast, in the group that trained their inspiratory muscles, this was the product that was used, they showed a significant reduction in the time to complete the 40-kilometer time trial. I haven't put asterisks on these bars, but this is a significant difference. And there's also a significant difference in the magnitude of the change between the two groups. The magnitude of the change was 4.6% IMT versus placebo. And just a reminder that that was a 6-week training intervention requiring less than 5 minutes per day of training. Now, in addition to the improvements in performance, we also observed improvements in or attenuation in breathing effort. So these are data on breathing effort for the training group during the incremental cycle test. The corresponding data for the placebo group, effectively the two lines lay over one another, so really not worth showing you that data. I want to show you the data for the training group, showing that after the intervention, the turquoise line, the ratings of breathing effort were significantly lower. Perhaps slightly more surprisingly, the ratings of whole body effort were also significantly lower at each of these intensities. Now, I haven't put asterisks on here because it just makes it slightly messy, but the only point at which there wasn't a significant difference was this point, which was peak exercise for whole body effort, which, because it was peak exercise and it was whole body effort, is always 10. So we have improvements in performance and a reduction in effort. Now, there have been a number of different studies of inspiratory muscle training in different exercise modalities. I've summarized a few here. These are studies that have used the pressure threshold inspiratory muscle training that I described earlier. So, for example, we have rowing time trial performance improved by 1.9%. This is the cycling time trial performance I've just talked you through. Running time trial performance improved by 2.1%. Swimming time trial performance 1.5%. This is the rate of this is the perceived rate of recovery during repeated sprinting, 7% improvement in that. And improvement in speed endurance performance. This is the yo-yo intermittent recovery test, showing a 16% improvement in anaerobic endurance. Now, some of you may be looking at these time trial performance numbers and thinking that they look a bit small. Of course, if you work in elite sport, you'll know that those numbers are not small. They're quite the opposite of small. And I can illustrate the magnitude relative to the margins of elite performance with this panel here. I've chosen this particular race to illustrate the differences, because it happens to be one of the smallest margins between gold and silver. This is from the Athens Olympics. It's the Coxless Fours. And across the rowing finals as a whole, the largest difference between gold and silver was less than 1%. The average distance was less than 0.5%. And the smallest difference was 0.04%. And this is what 0.04% looks like after 2,000 meters of rowing. And here we have Sir Matthew Pinsent in the stroke seat of the Great Britain Four. So when you stack these numbers up against these numbers, you begin to see that the improvements that result from inspiratory muscle training are relatively impressive. Now, I know what you're thinking. You're thinking, well, she's cherry-picked the data there. She's just chosen those studies that show improvements in performance. They're not as impressive as they appear. Well, you wait 20 years for a meta-analysis to come along, and two come along both at once. These were two meta-analyses of inspiratory muscle training that were published last year in healthy people. So we have systematic reviews with meta-analyses of specific outcome variables, two independently undertaken meta-analyses and systematic reviews, both confirming that inspiratory muscle training and respiratory muscle training generally improves exercise performance and a range of other different outcomes. Now, just focusing on performance and the systematic review by Illy et al., which is this one here. This is one of their summary slides, or summary figures rather, and what they've summarized here is the data for different types of exercise test. So these are constant power tests, remembering what Dr. Edward Winter had to tell us about the difference between load and power. Constant power tests, so this is a fixed intensity exercise challenge to the limit of tolerance. So those show a statistically significant improvement following inspiratory or respiratory muscle training. Time trials also show statistically significant improvement following inspiratory muscle training. Intermittent incremental running tests, so those are things like the yo-yo test, for example, also show an improvement following inspiratory muscle training. The kinds of tests that don't show improvements are incremental VO2 max tests. So incremental tests to, again, the limit of tolerance typically do not show improvements. And often the main outcome variable that's assessed in these tests is VO2 max, and I'll talk about why VO2 max doesn't improve in a couple of moments. So, even when we include the incremental tests that show no improvement following the intervention, overall the analysis supports the efficacy of respiratory muscle training in improving exercise performance. So let's just have a look at some of the other things that the meta-analysis concluded. As I've just mentioned, the benefits are observed following these three different types of test. They're not shown during incremental tests. All types of sport or exercise modality appeared to benefit, all those that were studied, so rowing, cycling, running and swimming. They tended to find that the longer the exercise test, the larger the improvement that was observed in terms of the benefit. And those participants who were least well trained, so least fit, benefited the most from the intervention, as perhaps we might expect. Okay, so I hope I've persuaded you with some fairly robust statistical data as well as a description of an inspiratory muscle training study that inspiratory muscle training improves performance and results in a number of other beneficial effects on things like perception of effort and inspiratory muscle fatigue, etc. Next question is, how does it work? Well, a number of studies have looked at various different outcomes, and when we look across these different outcomes, so everything from effort perception to heart rate and oxygen uptake kinetics even, when we look at these we can see that certainly for a physiologist there are some patterns of change here which are providing some clues as to what the underlying mechanisms for these improvements might be. Now, these again are studies that have all used pressure threshold inspiratory muscle training of the type that I described earlier. So most studies show that breathing and whole body effort is reduced. Studies also show that inspiratory muscle fatigue is attenuated, if not completely abolished. A couple of our studies have shown that breathing pattern is improved, so breathing becomes deeper and slower, more efficient. Now, I've chosen this phrase very carefully. Lactate turnover is improved. The lactate threshold itself doesn't change, and we published a study a number of years ago to verify this. So the lactate threshold doesn't change, so that's the intensity of exercise that corresponds to the accumulation of lactate. But the lactate concentration at any given intensity of exercise is lower following inspiratory muscle training. There are also some studies that have shown reductions in heart rate. Some of these are significant, where we have an asterisk that indicates that there was a reduction, but it wasn't quite statistically significant. Now this is hinting at perhaps a decrease in the level of the overall sympathetic activity that's present during exercise. And then most recently, a study showing that there is an improvement in oxygen uptake kinetics. So these are speeded following inspiratory muscle training, and I'll put a bit more detail on those data in a moment. So for me as a physiologist, there are a number of things leaping out at me in terms of potential mechanisms here. What I want to do before discussing those in more detail with you is just to exclude a couple. I'm going to explain to you why maximal oxygen uptake isn't the cause of the improvement, and nor is lactate threshold. Now, these are the usual suspects. When we think about physical training and improvements in performance, we normally associate training with improvements in VO2 max and or lactate threshold. Now, why does VO2 max not improve? Well, it's because when the blood leaves your lungs, it's already 97% saturated. The reason it's not 100% saturated is nothing to do with the lungs themselves. It's because there is shunting of blood from the venous side of the circulation to the arterial side without it having gone through the lungs. So there's some dilution, if you like, of the oxygenation. So it's 97 to 98% saturated. So ventilating more will not improve your oxygen carrying capacity. So we don't have to rewrite the exercise physiology textbooks to explain how inspiratory muscle training works, which is reassuring to say the least. As I mentioned earlier, we have also shown that the lactate threshold does not change in response to inspiratory muscle training. So, how does it work? Well, there's been a series of landmark studies that were undertaken at the University of Wisconsin by Jerome Dempsey's group. And although they weren't looking at inspiratory muscle training specifically, they were looking at the role of the respiratory muscles in exercise performance and in a number of physiological variables that were associated with that. I'm going to show you a couple of bits of information from those studies. Now, the paradigm for the studies was manipulating the work of breathing. They were able to unload breathing using this proportional assist ventilator, which effectively did the work of the inspiratory muscles for the participants. So the participants effectively relaxed their inspiratory muscles and allowed the ventilator to fill their lungs. They also increased the work of breathing by adding a respiratory or inspiratory resistance to the breathing circuit here. And they compared the exercise tolerance of individuals in response to unloaded and loaded breathing. And here's a summary of the performance data. They've plotted the control time to the limit of tolerance against the experimental time to the limit of tolerance. Here's the line of identity. The points falling below the line are those showing a shorter time to the limit of tolerance, and you can see that most of those are under the loaded condition. So if you make the work of breathing harder, you shorten the time to the limit of tolerance. Conversely, most of the points that are falling above the line of identity, indicating that the test is longer, are occurring in the unloaded condition. So manipulating the work of breathing affects the tolerability of exercise. So if you do some of the work of the inspiratory muscles for them, then you extend the exercise tolerance. Now, in another study, the same group looked at the effects of manipulating the work of breathing, again using this ventilator, on leg blood flow. And they did this using direct femoral arterial cannulations. So here we have the work of breathing. Here is an increase in the work of breathing on the right. and a decrease in the work of breathing on the left. And you can see that there is a reciprocal relationship between work of breathing and blood flow to the legs. So if you increase the work of breathing, you diminish blood flow to the legs. So to some extent, increasing the work of breathing is reducing the blood flow to the legs, and this led to the development of what's known as the blood flow steal hypothesis, which is that by increasing the work of breathing, you allow the inspiratory muscles to steal blood from the leg muscles. Well, that's only true if you increase the work of breathing. Under normal conditions, you wouldn't steal blood from your locomotor muscles with your respiratory muscles unless the work of breathing has been increased. So to some extent, this blood flow steal phenomenon is an artifact, if you like, of the model that was used to describe it. Of course, if you reduce the work of breathing, you are releasing some of the cardiac output, and that has the effect of increasing blood flow that's distributed to the legs. So the blood that was going to the inspiratory muscles is now able to go to the legs. Now, at a mechanistic level, how are these changes brought about? Well, the model that's been formulated to describe the underlying mechanisms is illustrated here, and it relies upon something known as a metaboreflex. Now, as the name suggests, it's to do with metabolism and it's a reflex. Now, all muscles, including respiratory muscles, have these simple nerve endings, unmyelinated nerve endings, group 3 and 4 afferents as they're known. And when metabolites accumulate within these muscles, they stimulate these nerve fibers, which send signals back to the cardiovascular control centers, and those trigger a reflex increase in sympathetic outflow. Now, that increase in sympathetic efferent discharge causes active limb vasoconstriction. It also causes active respiratory muscle vasoconstriction. So this efferent discharge is not specific to the locomotor muscles. It's occurring in all muscles. So the effect of this is to reduce blood flow to all vascular beds and cause an increase in blood pressure. So this is the scheme that has been proposed to explain these reciprocal changes in blood flow that occur in response to the work of breathing. Now, how do we think inspiratory muscle training plays a part in this? Well, we think that by training the inspiratory muscles, you increase the intensity of inspiratory muscle work that is required before this metaboreflex is triggered. And we have shown this, and others have shown this directly, that you can increase the threshold of work to a higher intensity before the metaboreflex is activated. So under sort of ecologically valid situations, for example, you either abolish the activation of the metaboreflex completely because the intensity of the inspiratory muscle work is below the activation threshold, or you delay it to a later point in the exercise, thereby maintaining the limb blood flow at a higher level for longer and improving exercise performance. Now, this is an important caveat, if you like, in that many people say to me, well, actually, my breathing doesn't really bother me when I'm exercising. But the perception of breathing effort, although it does affect exercise performance and reducing it will improve performance, having no detrimental effect on your performance from your breathing effort doesn't necessarily mean that your breathing is not limiting your performance, because if these metabolites are accumulating within your respiratory muscles, this reflex may operate even in the absence of any increase in breathing effort. So it's not just about how your breathing feels. These mechanisms are operating below the surface, if you like, irrespective of your perception. Now, another way in which these receptors, these afferents may influence performance is via an effect on central fatigue. And Marcus and Mann has recently published a review on this. We've known for a number of years that metabolite accumulation within exercising muscles can feed back, these afferents can feed back, and they can inhibit central motor drive, which means that in the presence of this afferent feedback, the magnitude of motor drive can never be maximal, and that has the effect of reducing muscle power output. So this feedback impairs performance. So the accumulation of the metabolites feeds back, reduces central motor drive, which impairs performance. Now we've just seen that we also have feedback from our respiratory muscles. We have this metaboreflex feedback, which of course is exacerbating accumulation of metabolites by causing vasoconstriction. But in addition, there is likely to be direct feedback from these afferents and the metabolite accumulation within the respiratory muscles themselves, again feeding back to inhibit central motor drive. So it's possible that these afferents are also affecting central fatigue, and of course if we can delay the activation of these afferents by the metabolites, then we may reduce or delay central fatigue. I mentioned a study a moment ago suggesting that oxygen uptake kinetics are accelerated following inspiratory muscle training, which suggests that these changes in limb blood flow are occurring very, very early in exercise. And here we have a figure from this particular study. You can see that within 60 seconds we have a speeding of the oxygen uptake kinetics. So this is after inspiratory muscle training. You can see that oxygen uptake is increasing more quickly in the post-inspiratory muscle training condition than it was in the pre-inspiratory muscle training condition. The magnitude of the VO2 slow component was also diminished in these particular studies. So this would have an effect, for example, on the oxygen deficit during exercise, and would impact on the oxygen debt at the end of exercise. And indeed, in patients with heart failure, a reduction in the oxygen debt post-exercise has been found following inspiratory muscle training. So these changes in limb blood flow and oxygen delivery are occurring very early in exercise. And whether or not this particular study, the phenomenon was due to a change in metabolite accumulation and metaboreflex inputs is open to question. We don't know. There are other potential mechanisms, but those are beyond the scope of what I have time to talk about today. So oxygen uptake kinetics are speeded. There's also some recent evidence from Louise Turner showing that reductions in the oxygen cost of breathing occur following inspiratory muscle training. And this again is our tried and trusted training regimen, as was the previous study that I showed you on the oxygen uptake kinetics. Here we have total oxygen uptake measured at the mouth under two conditions. The first condition is before the inspiratory muscle training. The second is after inspiratory muscle training, and these are three different levels of voluntary hyperpnea, so voluntary overbreathing. Under these conditions, an isocapnic state has been preserved with a CO2-rich mixture. What they also did was they partitioned out the respiratory muscle component of the total oxygen uptake, so we can see that the oxygen uptake requirement of the respiratory muscles is significantly reduced following the inspiratory muscle training. And so this is our training group, and this is our placebo group. Placebo group, of course, showing no change. So we've got significant reductions in the oxygen cost of hyperpnea following inspiratory muscle training. Now, another study from the same group which answers two questions. It provides further support for this reduction in the oxygen cost, but also answers a question that I'm often asked, which is whether inspiratory muscle training is beneficial for athletes with asthma. Now, asthma is the most common chronic condition in athletes. It has a relatively high prevalence, a higher prevalence in athletes than it does in the general population. So these are some data from, they're not athletes, but they're physically active people with asthma, again showing a reduction, this time in the oxygen cost of whole body exercise after the inspiratory muscle training. So this is the oxygen cost of the exercise after the training, the open circles, and this is before the training, the closed circles. And again, note that after the training, this is a time to the limit of tolerance test that the participants are cycling for longer. None of these changes are present in the placebo group. They also monitored the breathlessness using a Borg CR10 scale of the participants during the exercise to the limit of tolerance, and we can see here that the baseline of the baseline intensity of breathlessness or dyspnea in the IMT group, which is the closed circles, is significantly higher than the same corresponding measurement made pre-inspiratory muscle training. Sorry, is correspondingly higher than the measurement made post-inspiratory muscle training. And you can see that for the placebo group, there's no change. These subjects also had a lower rating of dyspnea or breathlessness before the intervention. Hence, there is a difference between these points and this point, which is the pre-intervention rating for the IMT group. So what we have is a reduction in and this is the end exercise time point, we have a reduction in the sense of breathing effort in our people with asthma post-inspiratory muscle training. So same sort of phenomenon as we were seeing in our athletes in our cycling study. Okay, so just to summarize, in my view, inspiratory muscle training is a winner. We know that it reduces perceived exertion, both from a respiratory and a whole body perspective. There's some very robust evidence to support that. We believe that one of the mechanisms contributing to the improvements in exercise performance relates to the optimization of blood flow distribution during exercise. These changes occur very early in exercise, but we need some further data to really be confident that this is what's happening, but it's reasonable to suppose that this is the case. We also have some emerging evidence that inspiratory muscle training reduces the oxygen cost of breathing. And it's possible, again, that we need some more research on this. It's possible that inspiratory muscle training may also reduce central fatigue. Now, just moving to some more practical aspects of inspiratory muscle training, I just wanted to share this particular analysis that I undertook a number of years ago with you. What I did was I found two studies, our cycling study that I described for you earlier, breathing training as it's known here, and a high-intensity cycle interval training study that had used the same outcome variable, 40-kilometre time trial performance. Now, we showed a 4.6% improvement in this, which corresponded to 2.76 minutes. In this high-intensity interval training study, they showed a 5% improvement, and the time trial lasted 3 minutes in their particular participants. A 4-week intervention for the interval training, 6 weeks for the breathing training. Now, the training for the high-intensity cycle training consisted of maximal cycling, so this is cycling at peak power output. They undertook 8 intervals, which lasted 2.4 minutes each. The total amount of time taken for each training session was 53 minutes. They did that twice a week and accumulated 106 minutes of training per week, additional training per week. We contrast this with the inspiratory muscle training. Here's our tried and trusted 50% moderate load, 30 breaths twice a day. Each training session lasts about 2 minutes. You do 14 of those a week because you're doing it twice a day. So you accumulate around 28 minutes of exercise per week. Now, of course, one of the things that this 53-minute session duration doesn't take into account is all of the clearing up, the pools of sweat underneath the cyclovometer, for example, the kit that needs to be washed, the showering that needs to take place. In contrast, again, 2 minutes, don't even need to get it into a sweat or even get changed in order to benefit to the same extent virtually in terms of improvements in performance. I'd argue that this is pretty much the easiest 5% improvement in performance that you can get, but I'll leave it to you to decide whether or not you agree with me. Now I'd like to just wind up the presentation now just by closing on some more practical aspects of inspiratory muscle training. Now there are certain positions in sports and certain requirements of sports that can lead to an impairment in breathing just purely from a mechanical perspective. So if we look, for example, at cycling in the aero position, our abdominal organs are a non-compressible mass. They tend to be pushed forwards up against the diaphragm in this position. You also have an increase in abdominal wall tone, which means that the abdominal wall can't be pushed outwards as easily as the diaphragm descends into the abdominal compartment, and all of this increases the work of inhalation and makes the work of breathing feel much harder. Now similarly, in the case of rowing, we have a situation where the anterior thoracic and abdominal wall the movement of this is impeded by the thighs. So it's possible that we can simulate these restrictions that occur in movement by positioning ourselves to simulate those whilst we are undertaking the inspiratory muscle training. Now you can do this on an ergometer, but equally if you don't have access to an ergometer, you can simulate the effect of having your anterior chest and abdominal wall restricted by simply changing your body position. Now I mentioned earlier about postural control, and the effects of the inspiratory muscles on the ability to balance are something that's really only recently coming to light. This is a study that I collaborated on with some people at the University of Leuven, and it's a slightly complex design, but I'll talk you through it gradually, so hopefully you'll be able to understand what's happening here. We have a force plate, we have a foam pad, we have ankle vibrators and back vibrators that allow the experimenters to disrupt the feedback that comes from these two locations and their influence upon postural balance. And the postural balance is assessed by the force plate. Now the force plate represents a stable condition, so the participant stands on the force plate directly, that's the stable condition. Alternatively, if they stand on the foam pad, which is placed on top of the force plate, then that's an unstable condition. Now this study looked at two groups, a group with low back pain and a healthy control group, and they were compared under stable and unstable conditions with and without vibration, so sensory disruption from those sites. And depending upon where you disrupt the feedback, you can obtain an index of what's known as proprioceptive weighting. So where is the proprioceptive feedback coming from? If it's closer to 1, then that's showing that most of the feedback is coming from the ankles. If it's closer to 0, it shows that most of the feedback is coming from the from multi-segmental sources, so the trunk and the ankles. So if we looked at the unfatigued conditions, so this is unfatigued from an inspiratory muscle perspective, and we look at the patients with low back pain, you can see that predominantly they're using signals from their ankles, and that whether they're standing on a stable or an unstable platform, it makes no difference. And that's primarily, we thought, because they're unable to use their trunk and feedback from the trunk in order to execute a multi-segmental postural control strategy. In contrast, our control participants, they use more information from their ankles when they're standing on a stable platform, but when you move them to an unstable platform, they begin to use this multi-segmental strategy, which is much more efficient than using the ankles. When we fatigue the inspiratory muscles, you see nothing much happens with our low back pain patients because they're not using the multi-segmental strategy anyway. But what happens with our control participants is that they become more like the patients with low back pain. So we fatigue their inspiratory muscles, and they're less able to rely on feedback and activation of muscles from the trunk, and therefore they resort more to an ankle-steered postural control strategy, which is less efficient and less effective. So this is evidence that the inspiratory muscles are involved in postural balance and the execution of an efficient multi-segmental postural control strategy. So what does this mean? Well, I would argue that it argues that we should be using functional training techniques if we want to optimize the benefits of inspiratory muscle training in a sporting situation. So challenging breathing and stability simultaneously in the same way that you would challenge arm movements with an elastic resistance, we are challenging respiratory movements with the inspiratory muscle trainer. Now, in all of these situations, often what people would do would be to hold their breath because they are unable to accommodate the respiratory and non-respiratory roles of the trunk muscles in these situations. And this is just three examples from any number of examples that are illustrated in my book on inspiratory muscle training in sports. But they illustrate for you how you can challenge simultaneously breathing and stabilizing and postural control functions in order to optimize the synergistic effects of the inspiratory muscles, or the synergistic contribution of the inspiratory muscles to those two functions. So just to finally summarize, inspiratory muscle training improves performance. There's now very robust evidence from meta-analyses and systematic reviews that that is the case. We know that it makes exercise feel easier, so even if you're not a high-performance athlete, then surely the fact that exercise feels easier has got to be a benefit. It also potentially means that you can exercise harder for any given intensity of work, and therefore for those who are interested in burning calories, as it were, then it perhaps represents a way in which you can increase the intensity of your exercise, possibly either reducing the amount of time it takes to expend the same number of calories, or expending a larger number of calories within a given period of time. There's also, I think, some evidence that inspiratory muscle training could reduce postural and stability conflicts that exist in terms of the dual roles of the inspiratory muscles, and there's some work ongoing at the moment to look specifically at this, especially in patients with COPD who have a higher fall risk than healthy people of a similar age. So the intervention is supported by science. We have an understanding of how it works, and as I mentioned earlier, to my mind, if you want to improve your performance, it's pretty much the easiest 5% you can get. Now, if you want to know more about inspiratory muscle training, I've set up this website to accompany my book on IMT, and you can find lots of free information at breathestrong.com. I also have a blog where I talk about all things respiratory related, and if you're interested in the clinical applications of inspiratory muscle training, you might be interested in my website physiobreathe.com, which was set up to support my book on the clinical applications of respiratory muscle training, which was published earlier this year. And with that, I will thank you very much for your attention, and I'll finish by reminding you that further information about breathing training is available in my books and websites.